Hi, welcome to our 11:30 press conference, Arctic Heating, 15 Years of Sea Ice Loss and Absorbed Solar Radiation Gains. To introduce the participants is Patrick Lynch from NASA Public Affairs.
Hi everyone, we have a briefing today that follows a little bit on the previous one. So just to introduce, first we're going to have Norman Loeb, Principal Investigator of the CERES mission from Langley Research Center. Walt Meyer from NASA Goddard Space Flight Center, Sea Ice Research Scientist, and Jennifer Kay from the Cooperative Institute for Research in Environmental Science at the University of Colorado. Norm?
Okay, Norman Loeb, NASA Langley. Some people are wondering why 15 years? Well, because there's a very special satellite called the Terra satellite that was launched 15 years ago tomorrow, designed as a 5-year mission, but it's still fully functional, which I think is quite remarkable in itself. It has 5 instruments, the CERES instrument, which we'll talk about today mostly, the MODIS, ASTER, MISR, and MOPIT instruments. They really are observing the Earth, many different parts of the Earth system, and I won't talk too much about that. The poles are observed by the Terra satellite 14 times per day, so this is a very nice platform for observing the poles over this period. CERES stands for Clouds in the Earth's Radiant Energy System. It observes how much of the sun's incident light is reflected by the Earth, for example, from clouds, from the surface, from tiny particles called aerosols. And it also measures how much thermal radiation is emitted from the Earth. So it's essentially giving us a measure of what's called the Earth's radiation budget. What we'd like to know now is, given that we very publicized results of looking at the sea ice coverage and how that's declined, do the CERES observations show any evidence of a change in how much solar radiation is absorbed over the Arctic Ocean during the 15-year period? So here's the regional distribution. Looking on the left, it's showing the change in absorbed solar radiation on the left and the change in sea ice fraction on the right from 2000 to 2014, looking at summertime, 70 to 90 north and over the ocean. And what's really interesting about this is that you are seeing increases in absorbed radiation, solar radiation. For example, Beaufort Sea and areas here by Russia. But what's really neat is that they're very nicely tied with the declines in sea ice fraction. And you might say, well, that's kind of obvious. Wouldn't you expect that? Well, not necessarily, because the radiation is also impacted by clouds. And so there's a real question about what is the role of clouds, sea ice, and what's their impact on radiation. So this is really telling us what the answer is. If you look at the Arctic-wide, so this is the Arctic Ocean average for 70 to 90 north, looking at the absorbed solar radiation and the sea ice fraction changes, you're seeing this increase in absorbed solar radiation, decrease in sea ice. And here I just have a scatter plot of the two, and you can see that with increase or decrease in sea ice, you get an increase in absorbed solar radiation. And the amount is about 10 watts per square meter, or about 5% increase in absorbed solar radiation. There's about a 23% decrease in sea ice fraction in that period. Now, one of the interesting things about this is, while the long-term trend is pretty clear in both of these, if you look at individual years, it's not so obvious. You can see a maximum in absorbed solar radiation in 2011, but there is no, the minimum here in sea ice actually was in 2012. And so year to year, you don't necessarily see a correspondence, and the reason is because other processes, for example, clouds and weather patterns, will also affect the absorbed solar radiation. So one of the things we've been doing very recently to try and get some more measurements over the Arctic to try and understand the sea ice, clouds, and radiation was a field campaign called the Arctic Radiation Ice Bridge Sea and Ice Experiment, or ARISE. And this took place in September of this year. And it was essentially aircraft measurements of the radiation at different levels in the atmosphere, together with temperature profiles, humidity profiles, some in situ observations and some cloud observations. And what's unique about this is that we really tried to time these flights with the satellite overpasses from Terra, Aqua, and other satellites. And so we're going to be really digging into this data set in the coming months. So now I'd like to pass over to Walt, who will talk more about the sea ice itself.
Okay, thanks, Norman. As shown, there's been an increase in the incoming absorbed solar radiation that's fairly well correlated with the changes in the summer minimum ice cover. But as Norman mentioned, it's not a one-to-one, perfect one-to-one correlation. And there are various reasons for that, one of which is clouds, but there's also changes in the sea ice itself. It's not just the sea ice that's disappearing, but the character of the ice itself as it melts through the melt season. And I'll quickly, just to show you kind of an example of the changes that you see over the course of melt season. Early on in May, for example, the Arctic is still pretty much ice covered, completely ice covered, except for some cracks in the ice that are from the ice motion. You can see those in the dark lines. But essentially, it's a very white, bright surface, high albedo. Very little of the sunlight that comes in is getting absorbed in this situation, even though the sun is starting to get fairly high into the sky. When you go on to June, things start to break up. You're at the solstice. The summer incoming solar energy is at its maximum. But there's still a lot of ice cover there. It's still maybe just starting to melt, but the ice flows are still quite white, still high albedo, still reflecting most of the solar energy away. But you're starting to get some openings in the ice cover and the dark areas there where you get the strong absorption of the solar energy. And then you see a big transition at some point, oftentimes in July, where you start to see melt ponds form. This is meltwater that pools on the surface of the ice, and you get a very distinctive blue cover here in this is an airborne image from another NASA campaign this summer, the Mabel, which was also flying up in the Arctic. But you can see the very distinctive blue cover of the melt ponds. This changes the reflectivity, the albedo of the ice cover quite significantly. It lowers it, and these melt ponds can absorb more of the solar energy and expand and increase the amount of energy absorbed, even though the ice cover is still there. And then as we get later in the summer into August, now the ice is starting to disintegrate. It's heavily melting. The flows are more grayish, lower albedo because they've been eroded and melted. The snow is all gone, and there's a lot more open water. And now you're absorbing more of the solar energy. But you're getting later into the summer, so the sun is starting to set in the Arctic. And as you get into September, this is when the minimum occurs, and you get very little ice cover, but it's starting to even refreeze at this point. This is a shot from the ARISE aircraft showing kind of that milky look is the new young ice that's just forming, but it's still very dark, and so the solar radiation is theoretically getting absorbed there, but the sun is quite low, and so there's not much energy left. And the key thing here is that this happens every year, but there's spatial and there's temporal variability. The timing of these is really crucial because depending on when these events occur relative to how much solar radiation you have coming in says a lot about how much solar radiation gets absorbed into the system by the surface. And one of the things that we can measure using passive microwave satellite data is the timing of the melt onset, the surface melt. And that correlates fairly well with the September extent. The earlier melt, you have, the more chance you're going to lose the ice cover during the summertime. This melt onset is oftentimes in, like you can see there, it's in the middle, early to middle of June in the central Arctic on average. That's right when the solar radiation, downwelling solar radiation is at a maximum. So a week here, earlier now, that's 7 more days when you have a lot of sunlight coming in that you can absorb that energy and a lot of energy coming in. And there's 3 years there I picked out. And one of the things with the passive microwave record, it gives us a longer term context. Well, a series will only have 15 years. We actually have data from 1979, so over 35 years of melt data. Another aspect that's very important is the thickness of the ice, which we can look at using the age. The older ice is thicker than the younger ice in general, and what we've seen is a loss of the thicker ice cover and the older ice cover over the course of the last 30 plus years. Again, I show 3 years there, example. The oldest ice is in white, and you can see very little of that is remaining here as of 2014. And the youngest ice, the 1 to 2 year ice, the seasonal ice that's formed just since the previous summer, is in purple. And just looking at a balance there on the left, essentially what we've seen is we've lost the oldest ice, about 1.4 million square kilometers, and that's been replaced by younger ice in the wintertime. So we still have 100% ice cover in March of this period, but we're set up now to lose a lot more ice because the seasonal first-year young ice is much more prone to melt completely during the summertime than the thicker and older ice. And so what we've seen is a transition from the older, being dominated by old ice to being dominated by young ice. And of course, as the ice goes away, that allows more solar radiation to be absorbed. And even the surface characteristics of the seasonal ice is different than the older multi-year ice. Melt ponds form more easily. They tend to be more expansive, have lower albedo on first-year ice and seasonal ice than on the multi-year ice. So that's certainly part of the equation here that's playing a role. But another big factor is the atmosphere, and for example, clouds. And Jen will talk about that.
Hi, good morning. I'm Jennifer Kay. I'm a professor at the University of Colorado. And I'm going to start by talking about clouds and how they may or may not have influenced absorbed solar radiation over the Arctic. So in 2013, I actually published a paper with Tristan Lecoyer looking at long time series of absorbed solar radiation, clouds, and sea ice. And what we noted in that paper was that there is no long-term trend in clouds during the summer. The clouds change with the weather patterns, so some years there's more clouds, some years there's less clouds, but there's no trend in the clouds. So you ask, why is that an important result? Why is that an interesting result? Most of the globe, the oceans, are covered with clouds. So I think your initial suspicion and knee-jerk reaction might be to think that if we lose some sea ice, expose some dark ocean, we're immediately going to have some clouds form over it, replacing one bright surface with another. Replace the bright sea ice with some bright clouds. That is not what we're seeing, and so instead we're seeing these increases in absorbed solar radiation at the surface. We are seeing clouds play an important role in year-to-year variability, and actually I was in a press conference in 2007 looking at that particular year, which at that time was a big record, not only for sea ice but for clouds. If you look at this time series, look at 2012, which is now the record minimum, you see it's not a huge record in terms of absorbed solar radiation. And that's because the clouds and the sea ice didn't go hand in hand to have that go down. So clouds are playing an important role in the year-to-year variability, but there is no long-term trend that we are observing that would allow this masking of the surface. So 15 years, it's been mentioned, why is that a big deal? I would say to a climate person, 15 years sounds about halfway there. Climate is usually defined as a 30-year average. And so, we're getting there. And these long time series of absorbed solar radiation in concert with the longer time series Walt mentioned for the sea ice are really helping us to understand the climate of the Arctic region. Another tool that we have are climate models. And this slide shows a project that was just completed this year with collaborators at the National Center for Atmospheric Research in Boulder, Colorado. And the goal of this project was to understand climate change, that's what many of you, I'm sure, are wanting to report in this room, in the presence of internal climate variability. There is a lot of variability out there, and to understand that variability, we need long time series, such as the one from Ceres, and we need models that help us understand the processes that are controlling what we're observing. This is what's called an initial condition ensemble. So basically, the only thing that's different across all of these different sort of replays of the 20th and 21st century is a butterfly effect in 1920. We just changed the air temperature at a round-off level. And it's amazing the differences in climate that you can get over the 20th and 21st century. This plot is really showing you the global warming, so the global mean signal, which is really averaging over a lot of that small-scale variability. But it's projects like these that I think will help us understand climate change in the presence of internal climate variability. So there's some related talks at AGU this week that I thought you all might be interested in. First, I'm convening a session this afternoon that's really focused on these initial condition ensembles and trying to understand what we are observing and how it reflects both climate change due to increased greenhouse gases in our environment and also internal climate variability. And in particular, I want to highlight a talk that's tomorrow, and actually the author of that talk, first author is Alexandra Yan, who's up here in the front row. The title is Internal Variability Limits Predictability of a Summer Ice-Free Arctic. And basically, I think if you ever hear from someone that the Arctic is going to go ice-free in 2015 or 2035, some exact precise, it's going to be September 14th, 2035 at 10:31 a.m. That's just not the level of certainty that you would ever expect from something that has this amount of noise in it. And Alexandra will talk about that tomorrow in a talk here at AGU, and I encourage you to attend her presentation. So just to sum it up, we are seeing increases in the amount of absorbed solar radiation over the Arctic Ocean that go hand in hand with the Arctic sea ice loss. We are not seeing a cloud trend that would explain this. The clouds, they vary from year to year, but they are not what's causing this. It's really the Arctic sea ice loss and also changes in the surface conditions. And really, we're halfway there to a climate record, but it's really these long-term records that are going to teach us what's going on in the Arctic and answer the important questions such as why. Thank you very much.
Hello? Any questions from the audience?
Hi, David Appel with Yale Climate Connections. I actually have two questions. One for Dr. Kate. Does the lack of a long-term trend short-term trend in clouds in the Arctic have any implications for the overall global cloud feedback effect?
Well, it's basically saying there's no summer cloud feedback in the Arctic.
Yeah. So can any of that analysis say anything about what might happen globally?
Well, the Arctic is a relatively small region. It's one that we care a lot about, and so we want to know what's going to happen there, for example, with Greenland and Arctic sea ice, but I don't think there's a global implication. It's kind of a non-story, but it's the knee-jerk reaction. It's amazing how many times I've explained this to people, and they say, oh, there's got to be more clouds. There's more open ocean.
And for Dr. Meyer, so in the last couple of years, Arctic sea ice has been generally increasing and getting a little thicker. Is there any reason why that's happening, or is it just random?
Well, I think the reason is that we didn't have we had a really extreme minimum in 2012. Then you grow the ice back. That's all seasonal ice, and so you had a very low overall thickness and volume. and it was so low, we didn't have as extreme conditions in 2013 or 2014, so more of that first year ice survived, aged, had its birthday, and went to second year and then third year. So that's increased the thickness, which we can see in the ice age, and we observed, there was some talks about the Cryosat-2 from ESA data that showed increasing thickness. But I think that's really attributable to the natural variability. There's going to be variability, as Jen mentioned, looking at 2 or 3 years, it really doesn't say anything about your long-term climate trends. And even 15, you're still only halfway there. So we have a long way to go for thickness. But I would say, that these types of swings are maybe a little bit surprising in the sense that we expect that the extent to change quite dramatically, but the thickness is generally considered to be more stable. But we're seeing this variability as well, but I don't think it means anything for the long term.
Any other questions from the chat?
So this is from Bas Denhand. He's freelance. Why does young ice have a lower albedo than multi-year ice?
Young ice, well, when it's first snow-covered, the albedo is essentially the same. But as the snow goes away, as I mentioned, the melt ponds more easily form on first-year ice. That goes, I don't want to get into too many details, but the first-year ice is more saline, has more salt trapped into it. It tends to be less hilly, and so it allows the melt ponds to form and spread out more, and so that gives you an overall lower albedo. So it's not necessarily the ice itself, it's what's on top of the ice and how that changes.
Any other questions on the chat? No? Any other questions in the room? Okay, thank you.